it is a theorem which says that closure of a closed set is closed and it is the smallest closed set containing A. That is, this is the theorem statement. That is, for any A subset of R, the closure of A closure, is a closed set. And it is the smallest closed set containing A. It is the smallest closed set containing A. Okay, this is the theorem. So, in order to prove the theorem, we have the proof. First, we have to prove that we know that A closure is the union of A and L, where L is the set of all limit points of A. Okay, this set of all limit points of A, L, first we want to prove that this L is closed. Our first claim is that this L is closed. Okay, so L is closed means some set is closed if we say that all of its limit points are inside L, inside that set. So in that sense, we want to prove that L is closed. That is, we want to prove that if X is a limit point of L, that is X is a limit point of L, then we want to show that X is an element of L. Okay, so we are taking X as a limit point of L and we are trying to prove that X is an element of L, so that we can conclude that L is a closed set. Okay, so for that, let X be a limit point of L. Okay, let X be a limit point of L. Okay, now we want to prove that X is an element of L. So that is, we want to prove that X is an element of L means that X is a limit point of A. X is an element of L. Instead of proving that is X is an element of L, we want to show that X is a limit point of A. So let us take X be a limit point of L. Then we have, by the definition of a limit point, for any epsilon, arbitrary epsilon greater than 0, there is a point, we can find a point y which is not equal to X and it is an element of V epsilon X intersection L. So we take, for convenience, we take epsilon by 2. So epsilon by 2. For any epsilon it is true, so it is true for epsilon by 2 also. So for any epsilon by 2 greater than 0, there is a point y which is not equal to X, which is an element of this epsilon neighborhood of X and L. Okay. And also from this we get y is an element of L. So y is an element of L means that y is a limit point of A. So y is a limit point of, we get y is a limit point of A. Y is a limit point of A. Again, if y is a limit point of A, then again by the definition of limit point, for every epsilon greater than 0, so we are taking for every epsilon by 2 greater than 0, there is a point z which is not equal to y, such that z is an element of V epsilon by 2 of y intersection A, because y is a limit point of A. So there is a epsilon neighborhood of y which contains points other than y. Such a point is z. So z is an element of v epsilon by 2 of y, and z is an element of A. Z is an element of A. Now, by the triangle inequality, we have mod x minus z is equal to, just I am adding and subtracting one y inside. So, x minus y plus y minus z. Okay. Which is less than or equal to mod x minus y plus mod y minus z, which is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. So we get that mod x minus z is less than epsilon. What it is means? Mod x minus z is less than epsilon means, which implies z is an element of v epsilon neighborhood of x. C is an element of, or Z is an element of V epsilon of X, that is epsilon neighborhood of X. And also from the earlier step we know that Z is an element of A also. Okay. So we get Z is an element of V epsilon A and Z is an element of A. Therefore Z is an element of V epsilon X intersection A. So what does it means? It means that X is a limit point of A. That is, one in the epsilon neighborhood of X and A, there is a point other than X. Z is also not equal to X. So there is a point which is inside the epsilon neighborhood of X and A. That means that X is a limit point of A. X is a limit point of A. So, since X is a limit point of A, it must be contained in L. That is, it must be in L. That is, X is an element in L. So, from where we started, we taken X to be a limit point of L, and our claim is that X is an element of L. Our claim, we have to prove that, we want to prove that X is an element in L. Here we proved that X is an element of L. So, L is a closed set. Okay. Next, we prove that a closure is closed set. That is our that is the theorem asked us to prove. That is, a closure is closed. For proving a closure is closed, we need that L to be closed. Okay, we will use this later, L to be closed. So next we want to prove that a closure is closed. Okay, so again of the same definition of a closure, that is closedness, that every limit point, if there is a limit point, it should be contained in that set. If the set is closed, if there is a limit point for that set, that point must be inside the set. So if X is a limit point of a closure, in order to prove that a closure is closed, we want to show that X is an element of a closure. So this is our claim. X is an element of a closure. Okay, so let us take X is a limit point. X is a limit point of a closure. Okay, so X is a limit point of a closure by the definition of limit point for every epsilon greater than 0. So we take an arbitrary epsilon greater than 0. There is a y which is not equal to X in V epsilon X intersection A closure. V epsilon X intersection A closure. So we get a y which is an element of epsilon neighborhood of x intersection A closure. But what is A closure? A closure is, as all you know, that A union L. So by putting this here, we get y is an element of V epsilon x intersection A union L. Okay, all of you know about this rule, that is distributivity of intersection and union. We have y is an element of V epsilon x intersection A union V epsilon x intersection L. Okay, so from here, which implies y belongs to V epsilon x intersection A and or y belongs to V epsilon x intersection L. Okay, that is the basic property of when an element belongs to A union B and A intersection B. Again, we consider these two. We consider this one as case 1 and this one as case 2. So in the first case, we have y is an element of V epsilon x intersection A. So what does it means? Y is an element of V epsilon x, which means that x is a limit point of A, because in the neighborhood of x and A there is a point which is not equal to x. So that means that x is a limit point of A, which implies x is an element of L, since L is the collection of all limit points of A. So x is an element of L, which implies x is an element of A union L, okay, which implies x is an element of A closure. So if we take y is an element of V epsilon x intersection A, we get x is an element of A closure. Hence A closure is closed. As the second case, we have y is an element of V epsilon x intersection L. So again, by the definition of intersection, which implies y belongs to V epsilon x intersection L. Okay, sorry. By the definition also, V epsilon x and y belongs to L. So y belongs to L, but actually we don't need this. Okay, I'm just erasing this. We don't need this. Okay, if y is an element of V epsilon x intersection L, what does it mean? As previous case, we can conclude that x is a limit point of L. It is because in every epsilon neighborhood of x intersection L, there is a point y which is not equal to x, which means that x is a limit point of L. Okay, x is a limit point of L. And from the first part of the theorem, we have proved that L is a closed set. So L is a closed set, and now x is a limit point of L. Combining both, what we get, x is an element of L. Okay, again, which implies x is an element of A union L, which implies x is an element of A closure. In both cases, we get x is an element of A closure. Okay, so A closure is a closed set. That completes the part second of the theorem. Okay, A closure is a closed set. Now finally we want to prove that a closure is the smallest closed set containing A. What does it means? We want to prove that a closure is the smallest closed set containing A. That means if any other closed set contains A, then it contains a closure. Okay, I'm just writing, that is, we want to prove that if B subset of R is closed and A is a subset of B, okay, what I am taking, any closed set which containing A, which contains A, any closed set which contains A, we want to prove that, we want to show that A closure is a subset of B. If you take any closed set which contains A, then it contains A closure. Okay, so we are taking B to be a closed set and A is a subset of B. We want to show that A closure is a subset of B. Okay, for that, in generally when we are proving for a subset, one set is a subset of another set, we are taking one element from the A subset of B. We want to prove that if A, in this case we want to prove that A closure is a subset of B. We want to take some element in A closure and we want to show that it is in B. Okay, so let X is an element of A closure. X is an element of A closure, but A closure is equal to A union L, which implies X is an element in A or X is an element in L. Okay, now X is an element in A. Okay, now we are considering this separately. Okay, if X is an element of A, then which implies X is an element of B, because we are assumed that A is a subset of B. So X is an element of B. Hence, what happens? From the first part we have taken that X is an element in A closure, and we end with X is an element of B. So A closure is a subset of B. Okay. In the next case, that is X is an element of L, which implies that X is a which means that X is a limit point of A. X is a limit point of A. Okay, so by the definition of limit point, for given epsilon greater than 0, there is a y which is, there is an element y which is not equal to x, and it is an element, it is in V epsilon x intersection A. V epsilon x intersection A. But A is a subset of B implies, we have taken that A is a subset of B implies that y is an element of V epsilon x intersection B. Okay, which implies what we get, that is y is an element of V epsilon x intersection B. Okay, so y is an element of V intersection V epsilon x intersection B means that in every neighborhood of x there is a point which is common to this neighborhood and B, the set B. What does it means? X is a limit point of B. X is a limit point of B. So again we are assumed that B is a closed set. So B is a closed set and X is a limit point of B. Combined together we get X is an element of B. So we started from X is an element in A closure, and in this case also we get that X is an element of B. Therefore A closure is a subset of, therefore A closure is a subset of B, So therefore a closure is the smallest closed set. Smallest closed set containing A. Hence the theorem. Okay, it is very important theorem.